Now we are going to look at one more coordinate system, right? Something known as polar coordinate system. So till now, if you remember when you're plotting the complex numbers, or even in your XY plane, right? Whenever you do this, you take a point which is say 3, 4 again. So let's say this is 3 and this is 4. What you do is you take the distance from the x-axis and distance from the y-axis, correct? So all your calculations is based on distance. So we mark this point, and this comes because of the coordinate. So this is 4, this is 3. Sorry, this distance is 3 and this distance is 4, right? So therefore, we mark the point 3, 4. In Argand plane, we can say this is nothing but 3 plus 4i. Correct. Now look at it in a different way. So when we are doing problems and when we are multiplying with I, we understood that angles are important in complex numbers. And if I multiply sufficient number of times for particular complex numbers at least, I'm going to get back the complex number, right? So what if instead of writing in terms of distance only, I write in terms of distance and angle? Okay. Now look at it. Now one way you might think I can write these two distance and this angle. But if you fix these two distance, right, your angle also becomes fixed. If you notice, for example, let me look at this point. Okay, 3, 4. Let me write this angle as theta, made from the positive x-axis. Okay. Now this distance we know because it's from origin, so it is nothing but root of 3 square plus 4 square. So this distance is 5. Okay, we already know that mod z, if this complex number is z, it's 5, right? Now, can you say that if I have a complex number, whose distance from origin is nothing but modulus, right? So modulus of the complex number is 5, okay? And it makes an angle, say, well, whatever this angle is, I'll write it as tan inverse because we know this angle. It's tan inverse of 4 by 3. Suppose I gave you this information. Can you tell me that this should be the complex number? Does that make this complex number unique? So I hope the question is clear. My question is, like 3, 4, when I say 3, 4, you're going to mark exactly one point in the entire plane, right? You won't be confused that whether this is the point or this is the point because it's fixed. Correct. Similarly, what I'm asking is, if suppose I fix the distance and the angle, that is, this distance is distance from the origin, okay, and this angle is made from the positive x-axis. Okay. If these two are fixed, can you still get the point? Yes, you can. Okay. Let's look at this. Suppose I change the angle. So obviously, it would be something like this. Suppose I change the distance. You can see that it will increase here. It will increase or decrease, okay, depending on what distance you choose. But you'll never come to the same point because if you change the angle even a little bit, obviously this line should be different. It can't be the same line. Correct. So just to look at it different way. So this is the line. So if I'm talking about 5 units, right? You can imagine just a circle continuous, right? There's a circle. So 5 units. So each of these points will have different angles, right? All of these will have different angles. So now you get the idea. So I can name a point with respect to the angle and the distance from the origin. I can't take any other distance just because it is a variable. So you might get multiple points from it. And from origin, it's from the center, so you'll get only one distance. So if it should be 5 units, right, you can see you can get a circle, right? So the distance is 5 units for all the points in the circle, but you can see that the angle keeps on changing. Okay, so each angle will give you a unique point there. Why is this important? Now, any complex number given, even though it's 3 plus 4i, I can write it in a different format. I can write in terms of modulus and this angle. Now the question is how to write it. Okay, so there's a particular form. Okay, I don't know if you have learned vectors, you might be able to guess. Suppose I mention this length instead of 5 as r. Suppose this is r. Okay, so let me write this complex number, or let me just change this, keep it as 5 itself. Take some other complex number. Let say this random complex number here. Okay, this is z. Okay, I don't know what is the coordinates. So I'll write it as a plus ib. A plus ib. Okay. Now look at it. So this distance here will be r. Suppose I take this as another angle as phi. Okay. Now, what is the relation between this a plus ib, what we write, and this distance and this angle? That's what we are trying to figure out. So this coordinate A and coordinate B, we know that coordinate A is nothing but, again, we are talking about a distance, right? All we are talking about distance. Distance from x and y axis, correct? So if this is A, so this distance would be A. So can you tell me what is A in terms of R and cos, R and the angle phi? Okay. So suppose this is 90 degrees. So what is cos phi? Cos phi is adjacent by hypotenuse, so A by R. So can you see that we got what is A? A is nothing but R into cos phi. Similarly, you can guess if you take sine theta or sine phi in this case, you'll get this is B, right? Opposite by hypotenuse. So B by R, or B is nothing but R sine phi. Now, suppose I write it in the form of a complex number A plus IB. A is nothing but R cos phi. B is nothing but R sine phi. Can you see the new form what we are getting? The complex number is nothing but R times cos phi plus I sine phi. This is important. So what I'm telling you is, suppose you have a complex number, it can be either written as A plus IB. This is when you know what is A and B. Okay. Suppose they give you the distance from the origin and the angle. What you can do is you can write it as R into, say, cos theta plus I sine theta. The usual angle what we use is theta. Okay. So whenever we say the argument, we usually use theta is tan inverse of y by x. Okay. Or in this case, tan inverse of, say, b by a. Okay. So we usually use the angle theta. Fine. You will see the applications here. There's one more form which you're going to learn, which is much more easier to interpret. You can understand what's happening, right? We'll come to that. Okay. Before that, this part should be clear. So these are called as your polar coordinates. Okay. So what we are doing, we are going to represent the same points in terms of distance and angle. Just to take a specific example, right? Just look at one of the points. We'll just try to write one of the points here. Suppose you want to write a simple point, say I. Okay. I is nothing but, if z is I, it means 0 plus 1i, right? Okay. So it's confusing. I'll simply write 0 plus I. That means the coefficient of the real part is 0. So it's on the origin. And this is 1. Okay, that's nothing but. Can you see what angle it makes? It makes 90 degrees here. Correct. So if I want to write the distance from the origin is 1 units. Correct. So what was our new complex number? It is R times cos theta plus I sine theta. If you want to write, you can write x coordinate and y coordinate separately. We can say that x coordinate should be R cos theta and y coordinate should be R sine theta. Basically, you're getting the same thing. Okay. The question is, for x coordinate, what is cos 90? It's 0. Okay. Now, can you see that it's 0? Because x coordinate is 0 here. We have only I. Correct. What is the y coordinate? Y coordinate is R times sine 90, which is R itself. Now, what is R? By distance formula, you already know this is 1 unit. So y coordinate is 1. Okay. Can you see that your polar coordinate is nothing but 1 times 0 plus I? In other words, that is nothing but I. We started off with I. We tried to convert it, right, by checking the angles and the distance, just to see that we are getting the same point. We got the same point. You can see one more example. Instead of taking I as a pretty obvious case, let's take some other angle which we know. Okay, say this point. So this point is actually, say, I won't tell you the point. Let's try to figure out what the point is. Okay, so I'll give you this angle. This angle is 45 degrees. Okay. Just to make it easy to find out. This is 45 degrees and this length is nothing but root. So what I have given you is R is 45 degrees. So let me write, R is length, right? So R is root 2. And the angle 45 degrees or pi by 4. Fine. So let us try to find the x coordinate. X coordinate is R times cos theta. R is what? Root. What is cos pi by 4? That is also 1 by root. Okay, 1 by root. So what is this? 1. So I got the x coordinate as 1. What is the y coordinate? R sine theta. Again, root 2 sine pi by 4, which is 1 by root 2 again. So we'll get 1 by root 2, which is 1. So what is x and y? So a complex number is nothing but x plus iy. And you see it's 1 plus I. Now just to cross check, you can see that this is nothing but a square here, right? What you're going to get. Correct. So 1 and 1. So this coordinate will be 1, 1. And you can see the distance will be the diagonal of the square, which is nothing but root 2. Right? There are multiple ways in which you can cross check the same answer, but you should be able to understand what we're doing with angle and distance. Okay, you can take any point here, but the problem would be you may not know the standard angles. I chose angles such that we know what is sine 90, we know what is sine 45, so on. So some standard angles it's easier to find. Others you need to use either a calculator or a log table, right, to get the values of sine. So now we are going to see the Euler's formula. Now, what we have just derived, that is cos theta plus I sine theta, the polar coordinates, right? The polar form. Now you can write this even in e power I theta. Right? I know it looks very different. How is e power something connected to a trigonometric function? Okay, we'll come to that. We'll look at the derivation. But this is the Euler formula. So what this makes is, it makes a problem much more easy to understand, right? What happens when we multiply angles, correct? So when we multiply two complex numbers, you can see the angles get added, right? We already did that exercise. But before understanding, let's try to figure out why this is true. What's so special about this form? Okay. So for this, you need to know much more. Okay, in order to derive this Euler's formula, we need to know a couple of series known as Taylor's or Maclaurin series. Okay. What are these series? These are nothing but infinitely long polynomial series. Okay. First of all, just so that there's no confusion, cos theta and sine theta are actually trigonometric functions. Okay. So we can't call them exactly as polynomial functions. But you can see that there's a way to write this as a polynomial, right? Infinitely long polynomial. Okay. So usually when I say a polynomial function, what I mean is where a n x power n is a whole number, or it's stopping at a point, not at infinity. Okay. Now, how can we write this? I'll just try to jot down the Taylor series. Try and see if you can understand what it means. Okay, it's not that important for you at this stage, right? But I'm just instead of simply giving the theorem, I'm just trying to derive it. Okay. So any function given, right? There's some prerequisites for this, but it should be continuous and differentiable. Okay. Otherwise, this won't hold because we are differentiating. Okay. In order to get this function at x equal to a, okay. So I'm trying to write the Taylor series at x equal to a. So all these series are written at a particular point. You'll see, you'll understand why. Okay. So what I do is I write f of a. Now look at this. If I simply put x equal to a, it's true, both sides, correct? F of a, because x equal to a makes both sides equal. Now I'll write in terms of the derivative. Okay. Look at this. I'll add f dash of, say, whatever this function is. I'll differentiate at a. Is it clear? I'll differentiate at a and multiply with x minus a. Just look at what I've done. Suppose I put f of a. So that is, if I put x equal to a, this term is anyhow 0. I'm not going to differentiate at all. Suppose I want to differentiate, what will happen? Assuming you know differentiation, okay. So if I differentiate this is a derivative of x. What is this? Derivative of this is 0. Agreed. What is this? This is f dash of a into derivative of the remaining part, which is nothing but 1. Can you see that at x equal to a, now this f dash of a will be equal to f dash of a, right? So I'm just extending the logic. What I'm doing is multiplying the derivative and the constant part. So once I differentiate it, those parts will be equal. That's the logic behind it. Okay. So I'm going to extend this logic for higher powers as well. You can look at it. So if I differentiate it twice, okay, if I differentiate it twice, so what I'm going to get is x minus a whole square. But there's a problem here. If I simply differentiate this, I'm going to get 2 into x minus a first time. Second time, I'm going to get 2. So I have to get rid of that 2. Therefore, I'll divide by 2 factorial. I can simply write it as 2, but you will understand very quickly why 2 factorial is required. Look at the next term. If I triple differentiate or differentiate it 3 times, what will happen? This is x minus a whole cube divided by, now it is 3 factorial or 6. Because if you differentiate 3 times, see, now let us try differentiating once. If I differentiate 1, this is 0. Next time, next term is f dash of a. The next term is double dash of a by 2 factorial into 2 times x minus a. Agree? The next term is triple dash, okay, 3 factorial into 3 into x minus a whole square. We have differentiated only once. Now I'm trying to differentiate again. Look at this. If I differentiate again, this is a constant now, the second term, that will be 0. So what will happen to the third term? Third term will be, say, f double dash of a. Now let me cancel this 2 off. Okay. So derivative of x minus a is nothing but 1. Next term would be f triple dash of a into 3 into 2 into x minus a. Okay. Now I think directly you can guess what will happen if I differentiate again. You can see that the first term was a constant, second term was a constant, so it's 0. And third term, nothing but f triple dash of a. Fine. So can you see that at x equal to a, when I put x equal to a, both the sides are equal. Okay. Now I think you are able to guess what the Taylor series is. It's just the extension of the same logic what we are trying to do. Okay. Now I'll simply continue this. So next term would be fourth derivative. Okay, just to write it down, we just simply write the Roman numerals here. Okay, you can write numbers also if you want, but it should be clear that it is derivative, not the power. Okay, so f of a. So this is fourth derivative of a. When okay, then this is x minus a whole power 4. I have to divide by 4 factorial. So can we write the general term? General term. So if this is the same rth derivative, okay, rth derivative. So obviously I have to raise it to the power of r, okay, and the denominator should be r factorial. But we can't stop there. This goes say infinitely long series. Okay, so if you need to prove why trigonometric functions is not a polynomial, you can use this series actually. You can use this series as a hint. Later I'll try to derive it. Okay. So this is nothing but your Taylor series. I said one more series, which is a Maclaurin series. Maclaurin series is nothing but the subpart of Taylor series. Okay. Instead of taking different values, that is x equal to a, we look at one simpler value, which is x equal to 0. What happens is the equations become very easy, and most of our functions, that is sin x, cos x, e power x, etc., can be written in that series very easily. So for the same formula, if I put x equal to 0, what I'm going to get is a Maclaurin series. Maclaurin. So it is Maclaurin series. Okay. I'll just simply put it f of x is f of 0 plus f dash of 0 by x minus a. Right? Now a is nothing but 0. Okay. So what will happen? Look at the series. Because a is 0, this will turn to x. Next term, f double dash of 0 divided by 2 factorial by x square a 0. Here it's divided by 1 factorial. Okay. This is divided by 2 factorial. Next would be by 3 factorial x cube. Now you get the idea. You can see how simple it is, right? So if you want to write the general term, you can write in terms of n also or r. It will be f r the derivative of f at 0, okay, x power r divided by r factor. Now do one thing, just to get an idea, correct? So we try to get the Maclaurin series for e power x. Okay. So what I'm going to do, I'm simply going to put this function e power x for all of this term and see what it is. Okay. See what series we're going to get. It's very beautiful, right? So e power 0 plus f dash of 0. So e power x is a function where if I differentiate this, so if I differentiate this, again I'm going to get e power x itself. Agree? So, so if I differentiate also, I'm going to get e power x, okay, into x divided by 1 factor. Right? Again, if I differentiate, again I'm going to get e power x. So I'll put e power 0 into x square by 2 factorial. So how many times I differentiate, I'm always going to get the same terms. Okay. So it will continue like this. So can you guess what the series is now? So e power x, so we have never looked at polynomials that way, right? So e power x, an exponential function, can be written as, say, 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial, so on. Okay, so you can see how the series is going. So e power x is nothing but this series. Now I can give you an exercise, okay, because we know the derivative of sine and cos. Try to find out using the Maclaurin series what is sine x and what is cos x. Okay. So I hope you have tried. So let us try to get sine x now. Okay, sine x in terms of this. So I'll write the equation as it is, sine 0. Okay. Now what is f dash of 0? Okay. First, you have to find the derivative of sine x. What is the derivative of sine x? Cos x. So it will be cos 0. Okay. Cos 0 into x by 1 factor. Next term, f double dash. That means second derivative. So it will be sine derivative is cos. Cos derivative minus sine. Okay. So it will be minus sine 0 into x square by 2 factorial. Right. Next term, we got minus sine x. So derivative of minus sine x is cos x. So minus sine will remain. So minus cos x. Or it will be plus minus cos 0 into x cube by 3 factorial. I don't think you need the next term, right? But you can always try to guess what it is. Okay. So minus cos x will go back to sine x. Okay. So after that, we'll get sine 0, okay, into x power 4 by 4 factorial. And so on. The pattern continues. Let's try to figure out what this is. Sine 0 is 0. Cos 0 is 1. So it is x by 1 factorial. Minus sine 0. Doesn't matter as long as sine 0 is 1. Next term is minus cos 0. So minus x cube by 3 factorial. Next term is 0. Again, wherever there's sine 0, it will be 0. I think you can directly guess the next number. It will be plus x power 5 by 5 factorial. Next is x power 7 by 7 factorial. So if you want, take some more terms, try to figure out the series. So what did we get? X plus x cubed by 3 factorial. If you want, you can write in numbers, right? Sorry, this was not plus. This is supposed to be minus. So it is minus plus x power 5 by 5 factorial. So, clear? Can you see that by simply differentiating the function multiple times? So one prerequisite was we know sin x is, right, a smooth curve. So we already knew it was a smooth curve and differentiable. So we are able to differentiate. We take a random function and you don't know whether it's differentiable. We can see what the flaw is, right? So we are not supposed to differentiate at all to get this series. Okay. Now, Can we figure out what is for cos x? Okay, cos x. I'll use a different color. So do we need the series? Okay, I can try to write it down here so that we can see. So cos x is cos 0. Okay. Now derivative of cos x minus sin. So it will be minus sin 0. Okay, into x by 1 factorial. Okay, here also you can see you get sin 0 multiple times. Derivative of minus sin x now, second. Okay. So minus sin x is minus cos x. So it will be minus cos 0 into x cube, sorry, x square, right? X square by 2 factorial. Now derivative of minus cos x will be plus sin x. So it will be plus, in place of x it is 0. So sin 0 into x cube by 3 factorial. Similarly, if you want, you can continue. So next will be x power 4. So sine derivative is cos. So cos 0, x power 4 by 4 factorial plus so on. You can continue. Let's just simplify. So this is cos 0, which is 1. Sine 0 is 0. Cos 0 is again 1. So it's x square by 2 factorial. The next term is say sine 0. So again it is 0. Next term, cos 0 is 1, so x power 4 by 4 factorial plus so. Can you see the terms now? What I'm omitting? 1 minus x square by 2 factorial plus x power 4 by 4 factorial, right? So next term would be minus. I simply wrote plus and left it. Can you see this series now? Can we compare something? Can we compare something? Look at e power x. Look at e power x. Okay. This was a series 1x x square continuous, right? Very easy to remember also. When I went to sine, I had a changing sign, but I had only odd powers. X power 1, 3, 5, so on. We'll continue. What about cos x? It had only even power. This is x power 0, which is 1. X square, x power 4, x power 6 would be next. So on. Can you see it? It takes all the terms there. Because if I add them somehow, right? We still have to figure out how to add them. Okay. If I add them somehow, they're going to fit in properly because all the powers are there. Denominator is the same. Only problem is with a negative sign. Okay. Now let us look at the function. What we are trying to prove. We're trying to prove that e power I theta is equal to cos theta plus I times sin theta. Okay. So we'll do one thing. We'll figure out what is this e power I theta. We know what is cos theta already. We'll multiply this I to sin theta and see whether both sides are equal. Again, both sides are equal, our proof is done, right? So we know what is e power x. It's here, right? So I'll just copy this. Use the same function. Say, let us simply paste it here. Now what I'm trying to find? E power, let me write in terms of theta so that our result also remains. So e power I theta. So wherever there is x, I have to put I theta. Okay. So 1 plus I theta by 1. Right. Now it is I theta whole square by 2 factorial. Then I theta whole cube by 3 factorial. Fine. Plus so on. It continues. Agree. Now what is e power I theta? Let us try to simplify. Okay. So I remains as it is, I theta. Next term would be I square. I square is nothing but minus 1. So minus theta square by 2 factorial. I cube. We already know this. Okay. So this I is I itself. I square is minus 1. That's how we start complex numbers. I cube is nothing but minus I. Because it is I square into I. Right? I square is minus 1. I power 4 is 1. After that, again, the cycle repeats. That means we'll go back. Right? We'll go back to whatever this is. I power 5 is I. So you can see that. We already had a method, right? We divide the power by 4 and see what the remainder is to get what is the value of I power, say 2000, etc. Okay, so I'll just directly write there. So I cube is minus I into theta by 3 factorial. Fine. What would be the next term? Next term is I theta power 4 by 4 factorial, just to get more terms. Okay? It is easier to understand. I power 4 is 1. So it is theta power 4 by 4 factorial. Next, if I want to guess, okay, it will be theta power 5. So it is with I power 5, okay, and by 5 factorial. I power 5 is nothing but I itself. So I'll get I into theta power 5 by 5 factorial. Then I just combine the terms and see what I'm getting. See, complex numbers, so I want to write in terms of A plus IB, correct? Just to equate it. We know we want to equate it to cos theta plus I sin theta. So constant terms or the real part. Okay. So 1 minus theta square by 2 factorial. This one. Then this one again. Plus theta power 4 by 4 factorial. So on. Okay. Did we see this somewhere? Did we see this somewhere? Right? This was nothing but cos x. Or in this case, this is nothing but cos theta. Agree? Remaining terms, let me just combine the I terms. So it's I into what is remaining? Theta. Theta minus theta cube. Okay, this is supposed to be cube. Okay. Theta cube by 3 factorial. Next is theta power 5 by 5 factorial. So on. Okay. It continues. Now this is plus I into, again, did we see this result somewhere? So can you see that it's nothing but here? So this is nothing but sin x. Fine. So what are you getting? This is I into sin theta. Can you see that we proved e power I theta is nothing but cos theta plus I sin theta. This is nothing but your Euler's form, right? It's very important. Let us take a couple of examples so that you understand what we are doing. Let me just write. Say, let us take this graph again. We just seen some examples, right? So we'll take similar examples and see what it means. So we had taken an example of say 1, 1, I think, correct? So let me just draw the 1, 1. So suppose this is 1 and this is 1. So this point would be 1, 1 or 1 plus I if you want to write it like this, okay? Now can I write this 1 plus I? This is equal to 1 plus I in the form e power something. How to write e power something? Okay, that is the confusion. Now the first problem what we face is cos theta can never be equal to 1, which is false. Okay, the first problem what we face is cos theta can never be greater than 1. Correct? For example, if this was 5 plus 3i, how will I make these two equal? Correct? It's not possible. Therefore, what we have done is we had defined our complex number z as r times cos theta plus I sin theta. Correct? Then only because we need the magnitude. Angle wise, it's fine. Cos theta plus I sin theta was giving you the angle, but not the magnitude. Similarly, if I multiply both sides with r here, this is going to give you the complex number. Okay. Now, are you able to figure out that this angle is nothing but the angle you have to write here? Okay. So let us try for this problem. What is r? This is equal to I plus I 1 plus I. Okay. So I want to try to figure out what is r and what is theta. Okay. So you can directly see r is equal to 1. And theta is nothing but tan inverse of y by so can you see what is r? We know what is r. R is nothing but modulus of the complex number, isn't it? Correct. So if I try to find the modulus of this, it's nothing but root of 1 plus 1, which is root. Great. So I want to write my z as r times cos theta plus I sin theta. Now you can see that in a z, we didn't have that root 2. I'll simply multiply by root 2 and divide by root 2. We'll understand why we are doing it. Because if you try to simply write in terms of theta, there's no angle where cos theta is 1 and sin theta is 1. Okay. Either cos theta is 1, that time sin theta will be 0. Okay. So you won't find a particular angle where both are 1. So what is this doing by taking r is making sure you get a theta which gives you the angle. That's all. Okay. So now can you see what is theta? Theta is tan inverse of. You can use this also if you want. Okay. I'm just going to use this because just to match the theta. Okay. So tan inverse of 1 by root 2 by 1 by root, or tan inverse of 1, which is pi by 4. That means this is root 2 times cos pi by 4 plus I sin pi by 4. And we have already seen this. We already wrote this complex number in terms of angle, which is pi by 4, and this as root 2. We already knew it is root 2 times cos theta plus I sin theta. Now I am telling you, we can write this as say root 2 times e power I pi by 4. Right? Using the same logic, instead of writing in this form, I can even write it in this form. Okay. So one more form you got. Okay, writing in terms of e power. Okay, same as cos theta plus I sin theta because we have already proved it. Okay. So this angle or this complex number now is nothing but root 2 times e power I pi by 4. Now one important note here, right? You remember we did all that exercise about multiplication, right? We multiply with I and saw what happened. Okay. Again, the same case, we can see what happens. What is I? First, let me write I. It's not 1, sorry. It's 0 plus I, correct? 0 plus I. Okay. What is the magnitude of this? Magnitude is 1 itself. Okay. So it's 1 into still 0 plus I. Okay. So we already know this. This is this point, correct? This point, the length is 1, the angle is pi by 2. So directly I can write this is nothing but 1 times e power I pi by 2. The angle is again made by the positive x direction. Now can you see what is happening? I try to multiply this everywhere, e power I pi by 2. Therefore, there was a shift in angle by pi by 2. If you're not able to figure out, look at any complex number, take any complex number. Let me write it as say some r1 times e power I into say alpha 1. Let me take this complex number as z1. Okay. Suppose this is z, okay. Suppose I multiply z1 and z, see what's happening. Okay. So the magnitude is remaining the same because it's r1. Other side magnitude is 1. Angle is e power I alpha into 1 times e power I pi by 2. Just combining the terms. R1 into 1 is R1. E power I alpha plus I pi by 2. It is nothing but new complex number. What you are getting is R1 times e power I into alpha plus pi by 2. Can you see that now? What we did exercise, we did and we got some point whose magnitude was same. Magnitude is same as Z1. Okay. Angle was alpha 1 before, now it is alpha 1 plus pi by 2. Okay. You need not take only this particular example of pi by 2. I told you multiplication, the angle always gets added, right? The argument of Z1 into Z2 is nothing but argument of Z1 plus argument of Z2. Okay. That also can be seen very easily here. Just look at it. Take one more complex number Z2. Say R2 into e power I alpha 2. Now when you multiply Z1 into Z2, what is happening? You're getting R1 times e power I alpha 1 into R2 times e power I alpha 2. Now can you see the magnitude is also changing? I told you the product of the magnitudes, right? We are going to take. So can you see this is nothing but R1 into R2? If the magnitude of one of them is 1, then the magnitude remains the same. Otherwise, it's a product of the magnitudes. So R1 into R2. And the angle is nothing but I alpha 1 plus I alpha 2. Right? So this is nothing but R1, R2 e power I alpha 1 plus alpha. Okay. So now it's very easy to see that when I multiply what's happening. So magnitudes are getting multiplied and the angle is nothing but getting added. Correct? So the new complex number what you get will have the magnitude of R1 and R2 and the argument is alpha 1 plus alpha 2. So we have to write in the polar form R times e power I theta. Okay. So it's very easy. So let me write R first. Okay. For each of them, let me write R and the angle. That's it. Then you can directly write. So what is R? square root of x square plus y square or a square plus b square, right? So in this case, it is root of, say, 4 plus 4, which is root 8. What is the angle? Tan inverse of y by x, correct? So which is nothing but tan inverse of 1, which is pi by 4. So what is our form? So it is r times e power I theta, or it's root 8 times e power I pi by 4. You can simplify root 8 and write it as 2 root 2 if you like. So that would be your final answer. Second, look at the second part. It's 1 plus root 3i. I'm thinking it's supposed to be 1 minus root 3i denominator. Okay? So 1 plus root 3i divided by 1 minus root 3. Now you may try to simplify by taking the conjugate and then getting, correct? Instead, what I'll do is I'll simply use the polar formula to get the answer. Okay. What is the numerator? Tell me. 1 plus root 3i. This I want to write in terms of r and theta. Okay. So r is root of 1 square plus root 3 square, which is nothing but 2. R is 2. What is theta? Theta is tan inverse of y by x. What angle gives you root 3? Pi by 6. Pi by 6 is 30 degrees. Pi by 3, 60 degrees. So it is e power I pi by 3. Now, numerator is nothing but twice e power I pi by 3. Without even calculating, I can write the denominator as 2 e power minus I pi by 3. How do I know that? What is e power I theta? It is cos theta plus I sin theta. Okay. Just look at what happens to e power minus I theta. It will be cos theta minus I sin. So can you see that these two complex numbers are same? It's just differing with the minus sign. That too for the imaginary part only. Okay, we already seen this when we talked about conjugates. Okay, so we had already seen if this is my complex number, the next complex number or the conjugate will be something like this. Okay, because what happens is imaginary part here it was positive, it becomes negative. Same thing is happening. Look at the angle. It was plus pi by 3. This can be plus pi by 3. So the negative part would be minus pi by 3. Okay, the angle is positive itself, but it's a negative direction. That's all. So can you see what the ratio is? 2 and 2 will get cancelled. This will be e power I. Pi by 3 plus pi by 3 now. So it is 2 pi by 3. That's a new complex. Third one. Now, till now, we didn't have so high powers. Okay, this is one of the most important advantage, right, of writing in I powers. 1 plus I. We already wrote this before. So r is nothing but root 2. Correct. So e power I pi by 4. You already seen this. Okay, r is nothing but root of 1 plus 1. The tan inverse of 1 by 1, which is pi by 4. Now this I have to raise to the power of 20. Okay. So now you see how easy it is to raise to the power of 20 in complex numbers just because of this theorem. Okay. What I'm going to get? Root 2 power 20 into e power I pi by 4 times 20. Okay. What is root 2 times power 20? It's root 2 is nothing but 2 power half, right? So it is 2 power 10 into e power I pi by 4 into 20. So it is 5 pi. Okay. If you want, you can simply and see what you're getting. But we are asked only to write in the polar form, right? So this would be your answer in the polar form. Fourth one, 5 plus 5 plus 5i whole power 5 divided by 2 plus 2i whole power 10. I think you are feeling like cancelling some of the terms there, right? If you want, you can do that. I'm not against it. Okay. Or we can directly try to write it down. Okay. Because we already use I 1 plus I, right? We'll try to use it. Okay. By simply taking 5 power 5 common, isn't it? And 2 power 10 common. What remains? It's 1 plus I whole power 5 and 1 plus I whole power 10. Easier to calculate. So it is what? Say 5 power 5 by 2 power 10 into 1 plus I whole power minus 5. Or you can write in the denominator. Now we already know what is 1 plus I. So we already calculated it. So it's 5 power 5 by 2 power 10 into, you can see it's here along with root 2. Okay, so this is your 1 plus I. So it's root 2 e power I pi by 4 whole power minus 1. Fine. So let's try to simplify now. So 5 power 5 will remain as it is. 2 power 10 again. Now root 2 power minus 5. Okay, we have to figure out what this is. Into e power I pi by 4 into minus 1. That's it. Okay. If you want, you can simplify a bit better, right? By writing all the 2 powers common. This is 2 power 10 into 2 power. This is 5 by 2 in the denominator. So 5 by 2. Okay. And this is nothing but into e power minus 5 pi by 4i. Right? If you want, you can combine that 2 power 10 and 5 by 2 and make it, say, what is 2.5 to 2 power 12.5, or you can write in terms of fractions, which is 25 by 2. Now, we have already got the problem in terms of e powers, or r into e power I theta. We have to convert it into our usual form. Okay. So let's do this directly. I write 1, 2, 3, and 4. Okay. So first one, r is already known. So r times I have to write it as cos theta plus I sin theta. Okay. So every problem, the same thing. E power I theta, this theta will go there and r will remain outside. Okay. Using Euler's form itself. So it is 5 times cos 2 pi plus I times sin 2 pi, isn't it? Because it is 5 e power 2 pi into I. Okay. So what is it? 5 times cos 2 pi is 1 and sin 2 pi is 0. Can you see that? It's nothing but 5, okay, a real number. Okay. Second one, 3 pi, right? The angle is pi. So it is cos pi plus I sin pi. Again, sin pi is 0. Again, you're going to get a real number. Cos pi is minus 1 plus 0. The answer is minus 3. Okay. So now you can guess when do you get a real number, right? So whenever the imaginary part is 0, so usually it is multiples of pi. Okay. The sign is 0 that time. Third one, root 2 times cos of 2 pi by 3 plus I sin 2 pi by 3. Okay. Now 2 pi by 3 is only about 120 degrees. You just need to know the value of that. Okay. So it's root 2 into cos of 2 pi by 3. First of all, second quadrant, it's negative. Okay. So it becomes 1 at pi by 2, then it keeps on decreasing. Okay. So this is minus root 3 by 2. Sorry, it's not minus root 3 by 2. It's minus half. Okay. So cos pi by 2 is 0, then it comes down. So minus half minus root 3 by 2. Then if you want to use your formula, you can use pi minus theta, cos of pi minus theta. Okay, anyways, sine of 2 pi by 3, it is same as sine of pi by 3, which is root 3 by 2 plus I times root 3 by 2. Now you can simplify it by multiplying by root 2, which is minus root 2 plus I by root 3 by 2. Right? Fourth one, e power 3i pi. There is no r, so it is easier to write. So directly I write in terms of cos theta. So it's cos 3 pi plus I sin 3 pi minus cos of minus 3 pi, which is same as cos 3 pi, okay, plus I sin of minus 3 pi. Now, do we know sin 3 pi is 0? Yes, because it's nothing but sin of 2 pi plus pi, which is sin pi. And this is minus 1, and this is minus of minus 1. You can see the numerator is 0. So denominator is 2, but it doesn't matter. The final Cartesian form will be 6. Most of them, we got it as say, real numbers. So it's simple. Just write it as r into cos theta plus I sin theta. You get your answer. Expressed in the form of x plus I theta. Now we can simply expand this because we want everything in the numerator in the form x plus iy. Correct. So denominator part, we know what we have to do. We have to get the conjugate somehow and multiply. Numerator part, I have to again simplify and multiply with whatever extra I have. Okay. So first we'll expand. 1 plus 2i whole square. So it's 1 square plus 2i square plus 4i. Denominator is 4 plus I square. Let me write I square as it is because I'm simplifying again. Plus 4i. Fine. What is the numerator? Numerator 1 minus 4. Okay, so it is minus 3 plus 4i. Minus 3 plus 4i. Denominator is 4 minus 3 plus 4i. Okay, they are almost similar. Okay. Now what I have to do? I have to get rid of the conjugate denominator. So multiply with 3 minus 4i. Okay. The conjugate should be always a negative of the imaginary part. Okay. So 3 minus 4. The denominator becomes what? 3 square plus 4 square, which is 16. Numerator, so minus 3 into 3 is minus 9. 4i into 4i within the minus sign. So it is minus into 4i square. So 4 square is 16. Minus into minus I square. So it is plus. So plus 16. Right? Remaining terms minus, say, plus 12 plus 12. So plus 24. Yeah. So that's it. So we can simplify it. Numerator is 7 plus 24i. Denominator is 25. That's our form. So you just have to select the option. So A looks, so a real part is 7 by 25. Imaginary part is 24 by 25. Now again, you have to express in the term x plus I by. Okay. So let's try to simplify it. A plus B whole cube. A cube plus B cube plus 3ab. So 3 into 2 into I into A plus B. Okay, you can even use the binomial theorem and directly write it, whichever you feel comfortable. Okay, 2 minus I, I'll simply multiply with the conjugate again because you have to get rid of the denominator. Anyways, this should be multiplied with the conjugate. Similarly, for the second part, instead of simplifying in multiple steps, we are trying to complete it. So denominator is 2 plus I. So the conjugate have to multiply in the numerator. So 2 minus I. So here 2 minus I. Remaining part is the A minus B whole cube, right? Or you can use A plus B whole cube formula itself. Just add the minus sign later. So it is 2 cube minus I cube. Okay. So it is 3AB. So there's a negative sign. So it is minus 3 into 2 into I. Okay. Into A plus B, which is whatever in this sign. So it is A minus 2. Now trying to simplify. This is 8. This is minus I. We know I cube is minus I. So this will be minus I. Then this is 6i into 2 plus I. I'll just directly try to multiply here. So what I'm going to get is plus 12i plus 6i square. 6i square into 2 plus I. The denominator you can directly write it is 2 square plus 1 square. So it's 5. Other side. Again, denominator is same. Numerator. This is 8 minus I cube. So it's minus I. So it will become plus I. Fine. Again, this is minus 6i into 2 minus I. So it will be minus 12i plus 6i square. Fine. Into 2 minus I. Now let us combine. So these two are imaginary parts. So it will be plus 11i. The real part 8 minus 6. So it is 2. 2 plus 11i into 2 plus I by 5. The other side So this and this will be minus 11i. And 8 minus 6 again is 2. 2 minus 9. Okay. Let's multiply it and write it in one line. So 2 into 2, 4. 4 minus 11. Okay, I'm just directly writing the terms. 4 minus 11 is minus 7. Right? And the imaginary part. So 11i into 2, 22i plus 2. So 24i plus 24. Right? We can multiply and check. So minus, because denominator is same, I'm directly going to do that. So minus 2 into 2 is 4. 11i into 11i is 11i square. So it is 4 minus 11. Okay. So again, the same thing you're going to get, minus 7. Imaginary part, minus 22i, minus 2. Okay. So minus 22i, so it's minus 24. Can you see the real part is the same? So if you subtract, you're going to get 0. And the imaginary part is 24 plus 24 is 48i by 5. So what you're going to get is 48i by 5 is option A. You could have done one more thing just to solve this problem. If you knew binomial theorem, right? So you could have written the conjugate directly. So 2 plus I whole cube. So you can directly multiply with the conjugate. So it will be 2 minus I into 2 plus I. So numerator will be again 2 plus I, correct? So nothing. This is nothing but 2 plus I whole power 4 divided by 5. On the similar plan, right? The second part, you can see we can do the similar thing, which is 2 minus I whole power 4 by 5. So if you know the binomial theorem, it becomes much easier and the terms get cancelled much faster, right? So you'll directly get your answer. Or else you can always use this. You can separately figure out and multiply with the conjugate and get your answer. So imaginary part, real part is separate and one more complex number is given. They're equal. So we know that if complex numbers are equal, right, both the real part and the imaginary part must be exactly the same. You can't have different answers. So this should be equal to 5 and this should be equal to minus 4. Okay. So one way is you can use the options, but it's not that difficult. So we'll simply multiply this by 2 and get the new equation 2x plus 4y is equal to 10. And we'll subtract, right? So subtracting, we get minus 7y is equal to minus 14 or y is equal to 2. So y is equal to 2 means x value you have to figure out. This is 4, so x is 1. So y is 2, x is equal to 1. Again, the logic is same. Okay, now we have to equate both sides. So again, real part should be same and imaginary part should be same. So x, right, we directly don't have any real part here. So you have to write both these sides in terms of a plus I. If both are written in that form, then only you can come back. So let me multiply with the conjugate. 1 plus 2i is 1 minus 2i into 1 minus 2. Okay. Next part is y into 3 minus 2i. The denominator is 3 plus 2i. So again, you have to multiply 3 minus 2. Other sides also I'll try to multiply the conjugate now itself. So it's 5 plus 6i into 8i plus 1. Denominator is 8i minus 1 into 8i plus 1. Okay. So denominators now all have become real numbers. Okay. We are getting rid of the complex part. So I'll write denominator separately. So it is 1 plus 4. So it's 1 by 5 into x minus 2xi plus 9 plus 4. So 1 by 13, right, into 3y minus 2yi. Okay. This is equal to, on the other side, 8 square is 64 plus 1 is 65. 65 into, now real part is 5 into 1 plus this into this. So it's 48 minus 48 plus 5 or minus 48. Imaginary part 6 into 1, 6 plus 40, 46, right? Okay. Now I just have to equate both sides. Let me just try to simplify the left-hand side even better so that I combine the real part. So it is x by 5 plus 3y by 30. Okay, this is the real part. Imaginary part. So let me keep I outside. So it will be minus 2x by 5 minus 2y by 30. So this is the imaginary. Right. So if you want, we can directly equate 1 by 65. This is minus 43. This is plus 46. So what is it? X by 5 plus 3y by 13 is equal to minus 43 by 65. Don't forget the constant part. Okay, others will make a mistake. So minus 2x by 5 minus 2y by 13 is equal to 46 by 65. Now multiply both the equations by 65 just to make it simpler. So you're going to get, say, LCM is 65. So this into 13. So 13x plus 5. So 5 into 3 is 15y is equal to minus 43. Okay. Second equation would be, you can divide by 2 first if you want. So this will be 23. Easier to do that. So this is minus 13x minus 5y is equal to 20. Two equations. Simply, I think adding them will give you the answer. Okay. So if I simply add them, so this is equation 1 and equation 2. Add them, x part will go off. So y part is 10y. This is minus 20. So this implies y is minus 2. If my y is minus 2, simply substitute in any one of the equations. 13x minus 30 is equal to minus 43. Or 13x is equal to, say, minus 13, or x is equal to 1. Sorry, minus 1, right? 13, minus 13 by 13. Okay. So your answer is y equal to minus 2. Oh, we don't have minus 2 in the options. Okay, I think one of the options is supposed to be so minus 2 and minus 1. So look at this problem. We're equating a complex number to something of a mod. So we know a mod is nothing but a real number, right? We're going to get a modulus or the distance from the origin. Okay. So what is the modulus of this? So cos theta plus I sin theta is the modulus. That means it's square root of cos square theta plus sin square theta, which is nothing but 1. So you have a complex number, and the other side your real number. So imagine part this should be equal to 0. That's the only case. So when is sin theta equal to 0? So obviously whenever sin theta is 0, cos theta is 1. Okay, so you need not worry about what this value is. Okay. So sin pi. Okay. So when sin theta is 0, cos theta should be equal to, cos theta should be equal to 1. Okay. If you take only sin theta equal to 0, you will get your answer as n pi, because each multiple of pi is actually 0. But in odd multiples of pi, if you check what happens is cos theta is negative 1. Okay. So what solution you are going to get is 2n pi. That means when cos is 0, 2 pi, 4 pi, you can see sin is 0 and cos is 0. Similarly, you can take the negative side, minus 2 pi, minus 4 pi, so on. Okay. So that is your generic solution set. So 1 plus I into z is equal to 1 minus I into z conjugate. And then what is z? So options are written in terms of x if it's c. So assuming what x is a real number, right? So I can write z as x plus iy. Okay. Just saying it's a real number. Okay. So what is it? 1 plus I into x plus iy. Okay. On the other side, I would have 1 minus I into x plus iy. X minus iy, because it's a conjugate. So let us see what relation we get. So we get x minus y. Imaginary part is xi plus iy. The other side, x minus y again. Imaginary part is minus xi minus 1. Can you see that the real part is anyhow is equal? Right? But imaginary part is not equal. The only way the imaginary part can be equal, okay, if this is 0. Because you can see that this is x minus y plus I into x plus y. The other side I have, say, x minus y into minus I x plus y. So there is nothing but a conjugate complex number. So there's only possible if, say, x is equal to minus I. Correct. So we are looking at the option, okay, where probably your real part is nothing but the negative of the imaginary. Okay. I think uh, here we have that case, and we have that case here. Fine. Both the case is saying that this is 1 and this is minus 1. But according to our exact complex number, what we got is, so it is x and z is minus y. So it is minus x into I. So it is x into 1 minus I. So the option should be right. So just by looking, you can see that only these two have negative of each other. Okay. But we have to check cross-check with the magnitude because we took the same example. So option B will be the correct answer. So we know that alpha square plus beta square is equal to 1. Okay, we're trying to find this complex number. Now, whenever we have anything in the denominator, looking at the options, we can guess that we have to just try to replace this by its conjugate and multiply it so that we get a real number, because there was nothing in the denominator in the options, right? So that's the usual approach anyways. So minus I beta. So multiplying with a conjugate means 1 plus alpha, it will be plus I beta. The numerator is the same, so I'll just simply make it whole square. What will happen to the denominator? Denominator is, this is real part, this is imaginary part. So it's 1 plus alpha square plus beta square. Agreed. Numerator, similarly, 1 plus alpha whole square plus I square beta square plus 2I beta into 1 plus alpha. Agreed. So let us look at what happens. Denominator, expanding 1 square plus alpha square plus 2 alpha plus beta square. Now we know what is alpha square plus beta square is equal to 1. We'll use that anyways. Numerator also we'll try to simplify first. So 1 square plus alpha square plus 2 alpha. I square is nothing but minus 1. So minus beta square plus 2I beta plus 2I alpha beta. Right? So denominator is, this is 1 plus 1. So it will be 2 plus 2 alpha. Numerator, constant terms we don't have. We have 1. We have alpha square, beta square. We have 2 alpha. And we have rest of the terms with the imaginary. Okay. So we can write either in terms of alpha or beta, because we know what is beta square. Okay. So we'll try to write it in terms of alpha square. Why? Because we somehow have to simplify this. Okay. Beta square is what? Beta square is 1 minus alpha square. But we need minus beta square. So it is alpha square minus 1. Right. Substituting it here, alpha square minus 1. So I'll get 2 alpha square plus 2 alpha minus 1, and this 1 will get cancelled. Okay. Rest is imaginary part. I into 2 beta plus 2 alpha. Can you see some things are common? So let me, everywhere 2 is common. So I'll remove 2. This is 1 plus alpha remaining. Numerator, alpha square plus alpha plus I times beta plus alpha beta. Again, 1 plus alpha is common everywhere. If you remove 1 plus alpha common, you can see that what remains. Here it is alpha into 1 plus alpha plus I beta into 1 plus alpha. Correct. These two will get cancelled. What remains is alpha plus I beta, which is option A. Okay. So this is a very important step. You can write it as alpha plus 1 plus alpha. You just have to figure out what is common. Okay. Once you figure that out, other hint was there was no denominator at all in the options. So that somehow should cancel. So you're trying to look at that factor, which is 1 plus alpha. A plus IB is equal to x plus IY whole power 1 by z. Right. This information is given. We have to find what is x by a and y by b. Because it's complex numbers, let's use the property and try to simplify it. Right? We know that real part should be equal to the real part and the imaginary part should be equal to the imaginary part. But we should be able to simplify before that. That's all. So because it is cube root, we'll take cube on both sides. Get this? So it's a cube now plus I cube b cube plus 2aib into a plus I. It's easier to equate now. Okay. Let me combine all the real parts. This is one of the real part, and if I multiply these two, I'll get the other real part. So it's a cube 2ab into b is 2ab square. Sine I square will be minus 1. Okay. Remaining is I. So this I cube is nothing but minus I. And remaining term is here. Okay. So I'll remove plus I outside. So it will be minus b cube. And this is 2a square b plus 2a square b. So what relation we got? We got x is equal to a cube minus 2ab square and y is equal to minus b cube plus 2a square. Why do we need this? We just need this to simplify this. Right, x is a cube minus 2ab square by a. Y is, what is y? Minus b cube plus 2a square b by b. You can see that a will get cancelled. So we'll get 2a square. So sorry, a will get cancelled. So it's a square minus 2b square. The other side, b will get cancelled. So it's minus b square plus, say, what is it? 2a square. Just simplify. It will be 3a square minus 3b square. One of the options. We suppose this option should be 3 into a square minus